Good evening, everyone, and welcome to the York Observatory's weekly TeleTube broadcast, the online astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. We are broadcasting live from the Alan I. Carswell Observatory located at York University in Toronto, Ontario, Canada. York YouTube broadcasts every Wednesday night at 7:30 p.m. local Toronto time. For any questions or comments you have of our past shows, or if you have suggestions for future topics, please send us an email at observe@yorku.ca. You can always connect with us on Twitter or Instagram with the handle at York Observatory and Facebook at Ellen I. Carswell Obs. I'm Maheen, and I'll be one of your hosts this evening, along with Arfa, Matt, and Austin. We also have Dr. Hyde join us today, along with a York PhD candidate Giang Nguyen as our special guest speaker. The topic for tonight's talk is exploring lava planets and their atmospheres. Before we get started with our main show, we want to give you a little update on what you can see this coming week. This week we have Vega, which is the brightest star in the northern constellation of Lyra, Altair, and Taurus, and asteroid 16 Psyche visible in the sky. There are some constellations that can be seen as well. These include Ursa Major, Bootes, and Cygnus. The Moon is in a beautiful waxing crescent phase tonight and has a visibility of 29.2%. Talking about planets, Mars, Jupiter, and Saturn are the three planets that can be spotted this week. Mars can be seen for more than 2 hours after sunset, while Jupiter and Saturn will be rising after midnight for those that like to stay up late. Most of these objects can be spotted with naked eye, however, you will need a small telescope to observe asteroid 16 Psyche. Happy observing for the week! We are very excited to be able to offer live imaging tonight. Because of the late sunset, that is, we are close to the summer solstice, we need to wait a bit before aiming the telescope at the sky. So live images will appear after the interesting talk by our guest speaker is over. Now, transitioning into our topic for today, I will now hand it over to Dr. Hyde to give us an introduction of our guest speaker who can enlighten us with what lava planets are all about.
Thank you very much, Maheen. This is Dr. Hyde. You will have to all please excuse the background noise because we are live at the 1 meter telescope on campus. That's the 1 meter Allen I. Carswell Observatory telescope. Very, very excited here tonight to be able to bring you some live images. And of course, we are trying at the moment, but it is just a little too bright outside still. So we're going to try at the end of this broadcast as long as the clouds behave. But before we get to any of that, we have a very, very exciting speaker tonight. Hope I'm coming through okay on the audio here. But let me go ahead and introduce our wonderful speaker, Giang Nguyen, who's actually coming to us also from York University in a way. He's a PhD candidate with Dr. John Moores at the university and came to York for grad school from McGill University and has a really fascinating background in lots of my own favorite subjects. Background in meteorology, so lots of fun rock facts, I suppose. And started in space studying the climate of Mars, which, as our regular listeners will know, is one of our favorite planets. And actually, I'm just going to give you all a tiny spoiler, so Maheen will have to forgive me here for just a second, but I'm going to steal the screen just to show you very quickly a sneak peek at the planet Mars. Now, Mars is in the process of setting in the Toronto area, so it is going down after the sun. It might not be high enough in the sky to view at the end of this broadcast, so I'm going to steal away here to show you Mars in the daytime. That's right, the sun is out, and we have the planet Mars coming through the 1 meter telescope. Very, very hazy. That's a lot of our atmosphere doing a distortion on the planet Mars. And this is coming in on the Malin camera, which you can see here. In the background, this is our own plane wave interface running the 1 meter telescope. And I thought for our speaker tonight, because he had studied the climate of Mars starting out, we could not do this without at least one image of Mars as for the live imaging. And you know, it's really quite wonderful work, of course, Mars, but that's actually not what this talk is about. So surprisingly, our speaker today went on to then go and study exoplanets and their atmospheres. So I suppose it's a small step from Earth to Mars, and a very, very large step out of our solar system to other planets. And with the recent discovery of a lava exoplanet K2-141b, which will be up just before the sun rises. So if you're really willing to stay up very, very late, you can, and you have a telescope, you can try to see this star. The planet, I understand, we will be learning more about, probably takes a bit more effort to detect, as I'm sure you will be hearing. So I'm going to go ahead and with this little picture of a hazy Mars fluctuating through from the 1 meter telescope, I'm going to hand off to our speaker, Giang, and say, please take it away and tell us all about these lava planets.
All right, hi everyone. So my name is Giang, and I'll be talking to you about lava planets and the atmosphere. And so to do that, I'm going to preface it with the discovery of exoplanets. So in 1995, the first exoplanet was found by a pair of Swiss researchers, Michael Mayor and Didier Queloz, and they discovered a Jupiter-sized exoplanet orbiting the star 51 Pegasi. And so this triggered a motion to further explore planets outside the solar system. And ultimately, their work earned them the Nobel Prize in Physics of 2019. And so from then till now, there's been a lot of missions sent forth by NASA and ESA, and as well as CSA, to find and characterize exoplanets. And so most notably ones are the Corot mission, launched in 2006, Kepler, which launched in 2009, and TESS, which launched in 2018. And so we have now detected over 4,000 exoplanets via transits and radial velocity methods. And so the transit methods involve the planet orbiting its star, and as it moves in front of the star, some of the starlight is blocked, so it dims. And that's essentially how we're able to detect if a planet's there or not. The radial velocity method takes into account the fact that a planet has its own gravitational tug, and as it orbits around the star, it will also tug the star in a smaller motion, and we can measure that and detect whether or not an exoplanet is around the star. And so now that we can detect exoplanets handily, the next step is to analyze what each one is like. And so transit searches have found thousands of stars, but only a few of them are lava planets. And so lava planets are rocky planets that orbit very close to a star. They orbit so closely that they are almost tidally locked, almost always tidally locked, and engulfed in giant magma oceans, such as our exoplanet 55 Cancri over here. And the temperature on these planets are even hot enough to vaporize rocks. So most of the exoplanets we found are actually hot Jupiters, and rocky Earth-sized planets are actually quite hard to detect. That's because they're really small, so they don't block a lot of the star's light, so it's hard to detect the dimming of the star. They also don't have enough mass to gravitationally tug the star a certain way, so it's hard to detect that. However, lava planets have a very favorable and extreme orbit that makes it easiest for us to detect. And so they orbit very close, so that means they block a lot of the star's light, and they also have more gravitational tug because it's closer. And importantly, their orbit are really fast, which means that in a relatively short amount of time, you can observe a lot of orbits. And so the more measurements you make, the more confident those measurements become. And so currently, lava planets are the best target for observing an exoplanet's atmosphere. A rocky exoplanet, that is. So I'm going to introduce K214b, which is among these lava planets. And among these planets, K214b actually has the most extreme orbit that makes it easier for detect. And so it was first discovered in 2018. It has 1.5 times the radius of Earth and 5 times the mass of Earth. And so it was first detected via Kepler. And in a follow-up research, researchers at La Silla Observatory managed to measure its orbit and its mass. And now that we know its orbit and its mass, what's next? Well, the next step is to explore its atmosphere. And using the upcoming James Webb Space Telescope, we may be able to detect the atmosphere and its many properties. So the atmosphere on lava planets is, of course, created from the evaporation of the magma ocean. And since these rocky planets are dominated by silicate material, such as quartz, the resulting atmosphere is a thin mineral quartz atmosphere. And so in this figure you see here, since the planet is highly locked, there is a permanent day side and a permanent night side. And so you will have a lot of atmosphere building up on the day side. And since there's a lot of atmosphere here and there's none on the night side, essentially, you will have a tendency for the atmosphere to flow from the hot day side to the cold night side. So my work in specific to K214b is that I create a computer simulation of K214b's using general fluid dynamics. So I determine things like the atmospheric temperatures, the wind speed, the atmospheric thickness, and then I test how future instruments can confirm the results from my work. So let's first start with the magma ocean. So here is a plot of K214b. So this is the day side, and the red part is the expected magma ocean depth. So you can see that in the middle of the day side, where it's hottest, the magma ocean can be as deep as 130 kilometers. And of course, as you move further away from the hot day side, the temperature gets cooler and the magma ocean gets thinner. The ocean flow is very slow and is expected to be less than 1 millimeters per second in terms of bulk flow. So the atmosphere on lava planets are partial, such that even though it's very hot on the day side, it's really cold on the night side. And the atmosphere pretty much condenses entirely when you get to the cooler regions of the planet. So here I show you, I'm showing you the pressure along the surface. So this is, again, the middle of the day side where it's hottest. So right at the substellar point, the middle of the day side, where the atmosphere is thickest, the pressure is only 6 kilopascal. And so if you compare that to Earth, which is about 100 kilopascal, the thickest part of K214b atmosphere is only 1/20th compared to Earth. And as you move into the night side, the atmosphere becomes so thin that it no longer behaves as a continuous body of fluid, and it transitions into a regime that's called the exosphere. So that's similar to Earth's own exosphere or the exosphere on the moon. Of course, there's weather, pretty extreme weather on K214b. So most notably is the wind speed, which is very fast. So here again is the day side. You start off with no wind, but the thing is that you're essentially evaporating silicon material into vacuum. And so there's nothing to slow it down. So it would just speed up and up until it reaches 4 kilometers when you get to the night side. As for precipitation, I've shown here is a plot of the condensation rate. So at the middle of the day side, where it's still hot, you have no condensation. It's all exclusively evaporation of the magma ocean until you get to the cooler part, and that's when condensation occurs. So if you're right here, this is where you get most of your condensation, and the max rate for that is per square meter. You're depositing about 12 grams per second of silicate material back onto the surface. So as you can imagine, the hydrological cycle revolves around minerals, mainly quartz, as opposed to water and earth. And this is really neat because the general public seems to have a very exciting perspective of lava planets. And so there's a lot of drive to research this further. But ultimately, how can we see these sort of extreme weather systems? Well, using spectroscopy, we can analyze the atmosphere composition and weather on K2-141b. So what is spectroscopy? Well, spectroscopy is essentially the study of light per color. And so light here is in quotations because I've expanded it to pretty much the electromagnetic spectrum. And each color simply corresponds to light at a certain wavelength. And so if we split up light, we can actually determine the individual contribution from each individual color or individual wavelength. And so I have here is the spectra, the stellar spectra of K2-141. You see that a little bit of the light is in the ultraviolet range. Most of the light is in the visible range, and the rest is in the infrared. And now each molecule, due to their unique structure, will absorb and emit very specific colors. And these are called spectral features. And so I have here is the absorption spectra or spectrum of our silicate atmosphere. And so it has what are called windows and curtains. And so windows are part of the spectra that light can go through the atmosphere without much impedance. So this happens a lot in the visible and near infrared, as well as other windows in the far infrared. And curtains are part of the spectrum that gets absorbed by the silicate atmosphere real well. So that's in the UV range and certain spectral features out here in the far IR. And so we can actually use this to pretty much detect an atmosphere. And so the first way is through emission. And so the hot atmosphere of K2-141b will actually emit a lot of infrared radiation, more so than the surface below it. And so if you just measure the light coming from the planet throughout an orbit at a specific wavelength, so at a specific color, you will get a much stronger signal at a silicate spectral feature more than any other part in the spectrum. And so this is what's called a phase curve. So this is just light coming that's measured from the planet. And I've plotted out the eclipse here. So the eclipse is when the planet actually goes behind the star and it's actually fully blocked from view. It's hidden, we can't see it. And I've also plotted out the transit. So this is when the planet goes in front of the star and the light you see actually dip even below zero because it's taken from the star. But the main point here is that at secondary eclipses, so that's when, that's the moment leading up to the eclipse, so around here and here, you actually get a noticeable difference of signal between the atmosphere and the surface below it. And so if you get a stronger signal at a silicate spectral feature, you would able to say that, there's an atmosphere there, or else we would be seeing the surface, which is a much lower brightness. And this also brings into the precision that you need to sort of distinguish it. So this is like a difference of 10 parts per million. So that means you have to sort of know that your planet, it's 10 parts a million brighter than what it's supposed to be. And that's how we're able to detect the atmosphere via emission. another part of observing the atmosphere is through transmission. So as during a transit, as K2-141b moves in front of the star, some of the star's light has to pass through the atmosphere. And so when you're at a window portion of the silicate spectra, so light from the star will go through it unimpeded, and you will get no blocking of the light. But the moment you hit a curtain part of the silicate absorption spectra, a little bit of the light will be blocked out. And this is actually important because this actually will tell you the composition of your atmosphere. And so this is called the transmission spectrum. And another cool part about the transmission spectrum is that you can use it to determine the wind speed. And so we do that by using the Doppler effect. So light passing through fast moving air will be augmented. So if your wind is blowing towards you and you're looking at an object with a certain color, the light waves coming from that object will be compressed because it's moving towards you. And so the object you see will suddenly turn blue, right? The opposite thing happens if the wind is moving away from you, the light waves from the object will be stretched and you will see that the object will turn red. And how does this translate into our transmission spectrum? Well, we have our transmission spectrum here, and with a certain amount of wind, it will turn blue. It will shift to the left. That's because the wind is going to be blowing towards the observer, and the light wave will be compressed, turning it blue. And so this is a pretty handy method of inferring the wind speed, and it should be easy to do, considering the wind is going 4 kilometers per second, which is very fast. And so hopefully I have convinced you that K2-141b is a highly valued target for exoplanetary studies. And so a lot of my work has been going towards making telescope proposals, trying to convince people to look more at this planet, and it was very successful. So the James Webb Space Telescope is a $20 billion NASA project due to launch in 2022. And in its first cycle of observing exoplanets and other things, K2-141b will be the first planet it will do so. And you should be excited, as I am, because K2-141b might be the very first rocky exoplanet where we can observe the atmosphere and the weather on it. And this is a very crucial step to pretty much finding habitable worlds and Earth analogs that are even smaller and colder. And so with regards to that project, I am not alone. I work with quite a lot of people, mainly with people from McGill and Oxford, but as well as people from NASA, Chicago, Oxford, University of Leiden, and the Max Planck Institute. All right, and so this is a wrap up. So I'm going to summarize my talk right here. So first I built a computer program that models the fluid flow on K2-141b with all the stellar radiation and surface radiation included. And so that produced a very warm atmosphere with very strong winds. And so during an orbit, we can observe the emission. And if we observe the emission at a silicate feature or a current part of the spectrum, you would get a much stronger flux from the ground below it. And therefore, you would be able to detect an atmosphere. You can also do the same thing with the transmission spectra, where light of the star has to go through the planet. And you will see which part of the spectrum goes through and which one gets blocked. And also with the transmission spectra, when you have very strong winds, you will get Doppler shift in your transmission spectra. And then you can infer your winds. And this has been done for hot Jupiters, but not yet for any rocky planets. And hopefully we get to see all of this with James Webb in 2022. And so that concludes my talk. I'll be taking questions if there are any.
As I recall, I believe we have several questions for our speaker. Looks like Arfa, you're first.
Yep. Thank you so much. It was really informative and really interesting. To be honest, I did do some research, but having the visual presentation and everything really, may develop more interest in it. But I have a few questions. So, like I noticed that the specific planet K2 141b is the major planet that we have been discussing or talking about. So I was just wondering that what makes this planet so ideal to study, and how is it like different and unique from other planets?
Okay. I can't remember if I mentioned this in the talk, even though it was about 10 minutes ago. But so K2-140b has the fastest orbit among lava planets.
Yeah.
So that means in a short period of time, you can make a lot of measurements. And so your measurements become more precise the more measurements you make. And there's also another part that, I'm gonna go back to my slide and talk about a transit. I could have sworn it was oh, here it is. Yeah, so the thing with K2-141b also is that when it transits, it pretty much goes through the middle of the star, which makes it ideal for transit spectroscopy, right? A lot of other planets will be at the edge, so you don't your time window of observing a transit is going to be much smaller. And so,
awesome.
Yeah, so that's why K2-140b is the best targets among the best targets to observe an atmosphere.
From this question, for example, like in our solar system, there is Earth, right? And then we know there are volcanoes here, and then there is ones on Mars as well. So can we predict that the other planets in that system may have the same terrestrial plane, or is it just too generalized of a assumption to make?
So are you saying that other planets in the system is going to be lava planets as well?
Yeah, like for K2.
So I guess this is sort of a misnomer. So when you think of lava, you think of volcanic activity, and lava planets are the lava part isn't from volcanic activity. We actually don't know anything about the interior dynamics of the planet. It's the fact that the planet is just so close to its star that part of it is just so hot that rocks have to vaporize. And so it's actually the proximity to the star that makes it a lava planet, not so much it's how it was born in the system.
So by any chance, can we predict that Mercury is going to be a lava planet someday, or no? Or is it just going to just evaporate or just be destroyed?
I'm guessing it has to, because the sun is expanding, right? So there's going to be, it's a long time away, but I'm imagining, before it gets swallowed, it will turn, into some sort of lava planet.
Okay, awesome. Thank you so much.
Wonderful, and I believe we have some more questions from a few other folks as well. We'll try to get through them as fast as we can. But Matt, I think you're next up for questions.
Yeah, so thank you as well. It was very interesting talk. First of all, well, this question, it kind of has been mentioned by Arfa, but in this case, by studying the atmosphere and the proximity instead of the volcanic activity of a planet, taking in account how ancient Earth was, like how hot it was, and how the volcanic activity in the atmosphere was here before life presented here, would there be a way to predict if a planet will be habitable in the future with that information?
Yeah, no, so that's a great question, because a lot of people I work with also make the argument that we should study lava planets because that's how Earth used to be. But the thing is that the Earth's interior dynamics is sort of a function of how it was created, which is by a bunch of rocks smashing together. And the rocks are randomized, and it takes a while for the heavier stuff to go to the bottom and the lighter stuff to go up top. And that actually creates friction, which is why the Earth's interior is so hot. So for K2-114b, right, this is just the fact that it's so close to the star that the surface is molten magma. And I don't think it will be habitable in any sense of what we know habitability is like. So I think that's the end of my answer. So I hope you're satisfied with that.
Yeah, no, it's more than enough for me.
Okay.
Thank you.
No problem.
Wonderful. And Matt, did you have a second question?
It was more or less the same, so I will give the word to Austin. I think he has a pretty good question as well.
All right, awesome. Austin, go ahead.
Thank you, and thank you, Zhang, for the presentation. I was wondering, in your study of exoplanets thus far, what has been most surprising to you? In particular, what do you hope to discover as you do future research?
What has been the most exciting or surprising?
Surprising or exciting?
So the surprising fact is that you only get a partial atmosphere. So the hope is that you will get an atmosphere that encompasses the whole planet, but it doesn't do that. Even though it's so hot, you actually need very hot temperature for quartz to exist as a vapor and not as a solid. The most exciting part about my research is, I think, the precipitation. If you go back to this CBS headline right here, scientists discover where it rains rocks, right? It rains rocks, but it also snow rocks. And I think that's a very interesting or a very fun thing to think about, especially if you think about a vapor, condensing as snow. Like, would you get quartz snowflakes on K2-114b? So that's what I think is exciting. So I think I fulfilled two parts of your question there. Surprising and exciting. Is there any more?
Yeah, absolutely. And then what do you hope to discover as you do future research?
Man, I want to see clouds. I want to see clouds on K2-114b. That would be quite a look, I'd say.
All right, well, that's probably a wonderful place to wrap up. We can definitely find you clouds here on Earth. We're at the moment at the 1 meter telescope going through a bit of clouds. Now, I think we're just wrapping up here. It sounds like we had a good set of questions. So I'm going to steal the screen, and we're going to go over to our promised live imaging. And we're just adjusting the focus real time here. So we'll be able to share that with everybody live. So let me grab this screen from you. And here we go, over to the 1 meter telescope. And let me just grab this. And there we go. So as you can see from before, we have our control screen hooked up. But we are no longer pointed at Mars. It's a bit too low on the horizon. And it doesn't look terribly good down there next to the sun anyways. So we have moved off to a binary star, and we're just trying a bit of focus on it. I'm just changing this number here, as you can see, this position number. We're going up a little bit in focus to try to battle through the fluctuating clouds here. You can just make out there are, in fact, 2 stars. And I'll just point out that I am not doing this entirely by myself. We are socially distanced, but Connor is here assisting me. So you may hear him once in a while as well. We're just reading out the attempt at focus. I believe our best was 99 something.
Yep, best was 9900.
9900 was our previous best. So I'm just going to go down a smidge back to 99. And it's probably anyone's best to guess if this is better or worse than what we had before. because as you can see, the atmosphere is bouncing around a little bit. So we're a little bit unfortunate in terms of just, I don't know, our atmosphere is extra bouncy. As you can see, even at a specific focus, it changes from sort of bad to good again. So this is definitely worse. I'm going back to 9900. Here we go. And this binary star, let me make sure I've got its name right. This particular binary star is Algeba, which I might be saying a little bit wrong. This star is a double star in Leo, which you can actually see the constellation lines on our navigation chart. This is a very nice bright double star, which is relatively easy to resolve, even at smallish telescopes, providing that your atmosphere isn't wobbling about too much. So this, as you can see, is the Malin cam. And we have a few different options here, which I'm just going to preload. We'll see if we can't bring it out a little bit more clearly for you. And we'll go ahead and pass it over to our co-hosts here to get a little practice on our live imaging. We'll take a quick round and everybody say their favorite binary star fact. Let's see who wants to go first. Binary, what's your favorite binary star fact? So I really love the binary star. Binary stars can actually basically get eaten by each other. I think it's kind of crazy the way they can evolve. Well, it looks like we actually have our telescope coordinator in chat, Quentin, saying it's kind of crazy to think, see, we're looking at the same sky. Yes, we are all, well, if you're in Toronto, this is the sky that you would be seeing. Can't get you a lava planet, but I can definitely get you two stars next to each other.
I have a binary star fact to share.
Go for it.
Well, it's quite interesting how sometimes it's really hard to see the second star. So sometimes they just appear as one star, and it's really hard to see the second star unless there's like gravitational influence of the other. So that's kind of mysterious, I feel like.
Yeah, that is, and especially if your second star is quite dim, that can really really play a big impact. It's actually fairly unusual to find them like this, where you can actually kind of tell that there are two stars here, despite, of course, the seeing. I think we'll go for a globular cluster, or maybe even we might go for a nice bright star, just to center and check our 1 meter focus. Of course, a really easy one would be to get something like Vega, and you see this changing in the background here. This is our camera trying to automatically adjust its exposure targets. All right, so there we go on auto adjust. And let's go up just a bit. And zoom back out. So this is zoomed in. I think we're just off center. There we go. All right, so we can see, of course, really bright stars fairly easily. This is the bright star Vega, which is actually one of the brighter stars in the sky at the moment. I don't remember if this was on your list, Maheen, for what's up tonight, but it's a great way to find your way around. So if you ever get lost or just want to sort of gain your place back and while you're stargazing, going to a bright star along the way is often a really nice one. So this is the brightest star in the constellation Lyra. I'm not sure if you can see it over the video, but it's just this little sort of trapezoidal sort of shape here. And Vega is actually relatively close. So Vega is only 25 light years from our sun. So 25 years ago, anyone care to do that math? So that would have been 1990.
96, I believe.
Okay, Connor says 1996, and I'm going to believe him. Never try to do speedy math late at night, folks. So 1996, what was playing on our TVs and in our radio is reaching the star Vega right now. So if you want to know what the star Vega thinks of us, it's what was happening in 1996. It's actually a really fun star if you're ever interested in sort of celestial dynamics. Up in the northern hemisphere, we have Polaris as our pole star, and Vega used to be the basically near the northern pole, about 12,000 BC or so. So this is quite a fun one. It will be the pole star again in the year 13,727. So we've got a little ways to go on that one. But for now, it is a nice bright blue star. And if I adjust this a little bit, I can bring out its features through the Malin cam. So this is our eyepiece cam. This is the camera that sort of best reflects how you would see these images through the eyepiece if we could get you up here to the 1 meter telescope. We're still getting a bit of background light. Of course, the sun hasn't quite gone down yet. And we'll go ahead and see what other kind of interesting things we can navigate to, because it's been a little while since we had such clear skies. How do the skies look out there, Connor?
They look pretty clear.
Pretty clear. All right, I'll take. There we go. Arcturus. So those of you who have heard the phrase arc to Arcturus may have been using a planisphere to guide yourselves around. Now, Maheen, I realize you didn't actually say Arcturus, you said Antares. I don't see Antares up at the moment. Let's see. Oh, there. Oh, it's too low on the horizon. So Antares is down here, all the way down at the edge of the eastern horizon. So our telescope can't quite point that way just yet. But Arcturus is another nice bright star. So arc to Arcturus is a handy guide you can use if you're looking up at the night sky tonight. Having the Big Dipper up there in the sky is quite easy to find. It's a very distinctive pattern, just down from the South Pole. And if you follow the handle of the Dipper out in the sky, you can follow that arc, so arc down to Arcturus. Arcturus is very, very bright, and we're actually picking it up quite nicely here with 14,000 counts through our Malin cam. Again, a nice bright star. Albireo is probably just a little bit too low to go to. I'm just going to give it one more try here because it's quite a fantastic double star. How are we doing? Nope, it is just a bit too low. We can, of course, try the Crescent Moon. But as I recall, it's a smidge hard to get it to show up. So what we'll do is I'll try to get the edge of the moon on there for you all real quick. And I'll just get that done again here. And we'll take a final call for any last objects that folks would like to see through the 1 meter telescope while we're running the TeleTube tonight. We do want to wrap up by 8:30 so that nobody turns into pumpkins. But that does, of course, mean that we miss the darkest part in our live imaging because the sun will be going down after 8:30. All right, so we have a lovely crescent moon out tonight. As you can see, the telescope is actually pointed towards the center of the moon. And due to our smaller field of view, we might get pointed into the part that is currently a bit dark. Let me just lower this target down. Whoa, you got just the very, very edge of the moon there. So I'm going to shift our position just a little bit. Just down on the side there, you can see a few little craters coming through on the moon. Of course, that is, as they say, the moon is a thin crescent at the moment, so it's not particularly easy to line up, but we're just going to do a short little shift in the position of the right ascension, I think I will do. So it's at, we're at 10:58, and we'll go down to 48, and just 0, 0, and then I'll go declination, same as where I am, so 11:38, and we'll go, sure, 11:38, 40. If I pull that up on the side, we should be able to see if it shifts that a little bit more. So go to, oh, we've gone just over onto the dark side of the moon. So we've gone that way, which actually worked last time I shifted that way. So we'll try going to 68. See if we can go back across an array. Let me just clear that so it doesn't think I'm trying to go anywhere else. Ah, yeah, okay. I see the problem. It's actually thought we wanted to go all the way across. So let's go back here. And there we are, back on the center with our little craters just barely showing there. And we want to put in yeah, 10:58. And we'll go down to 11:27. There we go. Turns out it was a declination shift. Ah, who knew? All right, so there is your crescent moon. We've got it for you. Beautiful cratering. That thin crescent moon is out tonight. So it's actually out right now, as you can see in Toronto. Lovely, lovely cratering. And we're actually, looks like we've captured the very, very tip edge of that thin crescent. Very, very fun. Unfortunately, our easy navigation is down at the moment. So you'll have to be happy with our slow shifts and declination. So you're watching right now a little bit of fluctuations from the atmosphere. The moon is in the process of setting, as you can see. It's going down towards the west, but it's pretty high at the moment. So here we are driving across the moon with the 1 meter telescope, just for you all on YouTube. All right, who's got some fun moon facts they'd like to share? Now, the moon is an easy one. I'm really looking forward to the lunar orbiting space station, the Lunar Gateway. I hope it does go out, gosh, next year? 2 years from now? You got a fun moon fact?
I spend all day looking at the moon. It's one of my primary research subjects.
Oh, okay, we've got an expert here, folks. So Connor spent all day looking at the moon.
Yep.
All right, just shout it out so the audio can pick you up here.
Yeah, I mean, my work is basically looking for ice at the lunar poles. It's sort of a tricky subject. Theoretically, it should exist, but the actual evidence is sort of spotty at the moment. So yeah, I spend my time basically, modeling the surface of the moon at these really small scales. Seeing, maybe there's these little tiny patches of ice. What's really exciting about the moon for me is the announcement a few weeks ago about a Canadian lunar rover.
Oh yes, the Canadian rover. That is.
Because they're going to be sending it to the South Pole, which is where there is expected to be, maybe some ice, so we can actually get some, actual evidence.
Oh yeah, well, and actually analyzing what the water on the moon is made of is going to be huge. That is so cool. And here we're watching this beautiful moon images go by. Arfa, it looks like you have a great moon fact. Go ahead. Oh, we're just catching her. You hear Arfa?
Right. Yep. So I have a few facts about the moon. So first is the moon is approximately moving apart from us 3.8 centimeter every year. So yeah, at one point it was going to be way distant than what is it now. And the second fact that I have for our moon is that it is the most widely accepted explanation that the moon was created is that the moon was created when a rock of size of Mars slammed into Earth shortly after the solar system began forming about around 4.5 billion years ago.
It is also very, very fun. Yeah, that is great. And of course, you know, this is one of the reasons I suppose why ice would be so exciting.
Yeah, I mean,
I'm sorry?
It's I mean, to expect to be, you know, some of maybe the oldest ice
Yeah.
that exists in the solar system.
Yeah, exactly. So just in case our audio is not coming through here, we're wearing masks as you're supposed to, but that does probably make us harder to hear. So we'll have to excuse anybody who can't quite make us out. The ice on the moon is particularly interesting because, of course, it might be some of the oldest ice in the solar system. If it somehow formed or condensed after the original formation of the moon from this big collision, well, that would make it quite old and potentially even primordial ice. All right, folks, we're just going to wrap up here. Looks like we'll be taking any last questions or moon thoughts that anybody would like to give. Just as a reminder, as we're rolling through here tonight with these beautiful images coming through from our Malin Cam, eyepiece cam, this is the Crescent Moon from Toronto at the LNI Carswell Observatory tonight. And I have to say, I really love crescent moons just for this exact reason. You can really see the detail and the relief on these craters. It's quite astonishing. So I'm going to try to see if I can get this to zoom out a little bit and make this cratering a little more visible. And we'll go up to 25, maybe up to 33. All right, so hopefully this is coming through even clearer now. As we approach 8:30, we are, of course, running out of time for this broadcast. I'm quite pleased this all worked. And of course, thanks so much again to our speaker for coming tonight. I am going to officially hand back over to Maheen. Maheen, if you can capture that screen share, we'll hand it over to Austin for our final send-off.
A special thanks to Giang Nguyen for joining us today and giving us a talk on exploring lava planets and their atmospheres, and also answering our questions. Well, everyone, you have been listening to the Alan I. Carswell Observatory's weekly TeleTube broadcast, the astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Arfa, Matt, Maheen, Dr. Hyde, and myself, Austin. Make sure to leave any comments or questions in the comment section of the video and talk to us in the chat right now. We'll be around for the next few minutes to answer your questions. All of our programs are free, but if you'd like to make a donation, see our website at observatory.info.yorku.ca. You can always connect with us on Twitter with the handle @YorkObservatory, and check out our website for show notes, content, updates, and contact info at observatory.info.yorku.ca. Thanks for tuning in. Clear skies and have a good night.